cord on this computer. I guess people can hear me. Remember, this is going on YouTube, so because of FERPA, we should, students should appear anonymously and silently and invisibly. I think that's perfectly absurd, but that's the Congress we've got. They've done worse things like vote to invade Iraq back in 2003. So what do you know? So let's see. I will start going through chapter 5 on series. I really, frankly, just between you and me, I'm not nuts about infinite series. I think they're kind of trivial. I mean, they either converge or they don't, and there are various obvious tests for convergence and divergence, and apart from that, it seems to me there's not much to say. So just a few definitions, and I made a graph, which I will show you. Here is the MATLAB, in fact, for the graph. I can move this over a little bit. So let's go through these definitions. If I've forgotten to do something or something's wrong, please send me a chat message to wake me up. I hope you can see the two screens. Is that right?
Yes, we can.
Great. Okay. Basically, we all know, of course, what a partial sum is, a sum from 0 to capital N of C sub n. And we call that a partial sum sub n for n plus 1 terms. And it converges to a number if for every positive number, no matter how small, there exists an integer such that if you sum beyond that integer, n of epsilon, your partial sum is closer to S than is within epsilon of S. And then S is said to be the limit of the convergent infinite series. Some series converge, others don't. They either wander or oscillate or diverge. And if, on the other hand, the absolute values of the terms converges, then we say the series converges absolutely. If it doesn't converge absolutely, but nonetheless converges, we say it converges conditionally. There's an example. A more interesting example is 1 over k. This gets smaller and smaller, so you'd think it might converge, but you can see that it doesn't converge if you group the terms like this. And then you can see that each of these terms is greater than a half. And so the series clearly diverges. This is a series that the Greeks thought a lot about. That was back when here in the Western tradition, we think of the Greeks as semi-divine because of Sophocles and Plato and so forth. But in fact, the Indians and probably the Chinese as well were understood things like this, I think, better than the Greeks. For one thing, they developed algebra. I don't know, it might have been Arabs and not Indians, or maybe it was Indians, I don't know. Anyway, the point is these other cultures, before Western Europe got moving around 200 years ago, the other cultures were actually ahead of us. Let's look at an important example. This is a crucial example, and it's almost all you need to know. What's called a geometric series. And if you just consider this product, you take 1 times this partial sum, and you get, of course, 1, and then you get all of these things. But then if you take minus z times the partial sum, well, you get this part here with a minus sign, and the only thing, and so you get a huge cancellation. The only things left over are 1 times 1 and minus z times z to the n, so you get this. That means that the partial sum from 0 to n of any complex number raised to the nth power is this ratio. This is so important that I made I put it in the examples PDF over here, and I even developed a MATLAB plot this afternoon. This MATLAB example, I think will help those of you who haven't used MATLAB very much. And you see in this example how to do this. If you send me a chat message, I'll explain this in more detail. Otherwise, I'll just say, you know, puzzle over it, copy it, enter it into your copy of MATLAB, play with it, and so forth. In particular, I encourage you to change the first z and change the second z. Here I'm doing n summed from 0 to 100. Here are the plots, and those are the plot commands up there. Hold on means that you put both plots in the same graph. So here's the case where z equals a half, and you see it almost immediately converges on its value, and the infinite value for z equal to a half is 1 over 1 minus a half, which is 2. And so if you can see that this is approximately 2 here. On the other hand, if you take z equal 2, this thing is going up like nobody's business. And in fact, the value for n equal to 100 is essentially 2 to the 100 and 100th power, and that's a huge number. This graph, I just stopped at 100 so that this thing, so the Convergence series would be valid. By the way, I find the examples and the explanations in MATLAB just atrocious. They give a trivial example, and then sometimes they give a super complicated example, but they just never give an example that's useful to me. It's really kind of annoying. So you can play with this further and add other plots for various values of z. For example, you could choose z equal to 0.9 or 1.1. In fact, if you want, I'll do this on the fly. So let's see if I can do this on the fly. Okay, so let's see. So I'm going to then I'm going to grab all that. In fact, let me show you in the screen so you can see it. So I'm grabbing all of that, copying it here, and I'm going to set this equal to 0.9, say, and we'll make it, say, green. And let's just see if this works. I'm doing things this fast, one can screw up. All right, there's the graph. You see, it also converges, but to a larger number, namely something like, it looks like 10. And on the other hand, we can grab all these, copy, paste, and make this to be 1.1. And now not green, what do we have as colors? So down here I can say help plot and get some suggestions. So let's do magenta, I like magenta. So I'm gonna do magenta, run. There we are. Okay, that's a much nicer plot. So let me let me run this example again. Typeset. Boom. Okay, so now in examples, it looks like this. So that illustrates the geometric series. Now, why is it that I said the geometric series are essentially all you need to know? Well, not all you need to know, but they're the most important thing in this, one of the most important things in this chapter. And it's that these things are, this is an example of a power series. And an analytic function in general is a power series. Here the coefficients are all 1, but in a power series, a general power series, the coefficients here are arbitrary complex numbers. Okay. One useful approximation that beloved by graduate students in physics is 1/1 plus or minus epsilon is 1 minus or plus epsilon, epsilon being a small number. Here it's z. I think I should have changed to epsilon. Well, let me try to make a note of that. It makes more sense. Test of convergence. Well, Cauchy, or Cauchy, of course, was always right. And he noticed that instead of this, this test, and what's awkward about this test is you can't apply it unless you know what the limit is. So, so the useful test is Cauchy's or Cauchy's, and what he said was the series converges if there's for every epsilon greater than 0, there's an integer such that for n and m both bigger than that integer, the two partial sums differ by less than epsilon. And that's equivalent. I'm not going to prove it. You can prove it. Maybe some of you can prove it in your heads, but I'm gonna skip that. But now you see this is very useful because all you need to do is, all you need to know what the partial sums are. You don't need to know what the exact limit of the series is. There's also a comparison test, which is kind of obvious. If you have a convergence series with positive terms and you have some numbers such that a series with numbers such that their absolute values are less than this, then clearly this series C sub n converges. And not only does it converge, but it converges absolutely. Because the absolute value of the Cn is always less than that, and this converges. So there you are. On the other hand, if we have two series and they're both positive, and the B series is bigger than the C series and the C series diverges, then so does the B series. The Cauchy root test is take the limit, or no, it's not quite like that. It's rather that if for some big number n, the numbers C sub n, an absolute value raised to the power 1 over n are less than or equal to some number that's less than 1, for all little n bigger than big N, then indeed we have absolute value of Cn less than x to the n, and of course x to the n is this geometric series that we've been talking about. By the way, it's called a geometric series because it's a power series with all the coefficients equal to 1. That's why it's called a geometric series. And we know that that thing sums to 1 over 1 minus x. So if this is true, then for large n, these things are smaller than that, and this converges absolutely. D'Alembert had another test, namely if the limit of the absolute value of the n plus first term divided by the nth term is some number r less than 1, then it converges, and it diverges if r is greater than 1. There's also something called an integral test, namely if you can find a function that sort of interpolates between the coefficients Cn and Cn plus 1 like this, and you can do the integral. If it converges, then the series converges. And then, of course, what you can always do is you can use one of your numerical programs, either a programming language like Fortran or C, or a higher level language like Python or Sage or MATLAB or Mathematica, and you just sum the first n terms of the series and try n equal to 100 or 1,000 or 1,000,000 or whatever, and see what the thing looks like. And that tells you that gives you it's not a proof, but it gives you a good a strong hint as to what whether the thing converges. I see a chat thing here. Yes, please do this on the fly. What do you want me to do on the fly? I need to put the chat thing closer to where my eyes are. Oh, that was the plotting earlier. Okay, no worries now. Okay. All right, so convergent series of functions. Well, it's very much like just a series of numbers. You have a sequence of partial sums where you are summing up these functions, f1 or f0, f1, f2 of z. And the sequence of partial sums converges to a function on a set D if for every epsilon greater than 0, every complex number in D, there exists an integer depending on epsilon and z, such that the limit minus the partial sum is less than epsilon for n greater than n of epsilon and z. Now these numbers s of z, which are the limit, and z can be either real or complex. And the function s of z then is said to be the limit on D of the convergent infinite series of functions, like that. We say it converges uniformly if you can choose n independent of z. So you've got this convergence for all n greater than n of epsilon, no matter where z is in the set D. And it turns out that the limit of an integral over a closed interval of a uniformly convergent sequence of partial sums of continuous functions is equal to the integral of the limit. And by the way, if you have continuous functions that converge uniformly on a closed interval, then they converge to a continuous function. A real or complex valued function of a real variable x is square integrable on the interval if the integral exists. The integral of the absolute value squared exists in either the Riemann or Lebesgue sense, and is finite. A sequence of partial sums of square integrable functions converges in the mean to a function as if this is true. So this is convergence in the mean, namely that the absolute value squared of the difference integrated over the interval go as you take n to infinity, that has a limit of 0. And sometimes instead of having this simple definition, we put in a weight function that's non-negative. And so that's a more complicated definition of convergence in the mean. And if the functions are real, then you don't need absolute value squared. You can just square it. Okay, now power series. As I said, a power series is a geometric series, but with arbitrary coefficients. So it's no longer geometric, actually. If you apply the ratio test, then you see the n plus first term divided by the nth term is absolute value of z times the ratio of the C's. And this will have some limit. And if we call the limit 1 over r, and if 1 over r is less than 1, which is to say that z is an absolute value less than r, then we have convergence. And another definition of r, if you just rewrite this equation, you see that r is the inverse of the limit of this ratio. And within this circle, the convergence is uniform and absolute. And of course, an example is the geometric series. This has Cn equal to 1. And so the limit of Cn plus 1 over Cn, well, it's a limit of 1, and that's 1. So r is 1. And so then by the ratio test, it converges for absolute value of z less than 1. And that's pretty obvious here because, in fact, that's what we saw here. This was 0.9 and this is 1.1. So this is, okay, there was a question here. Are any of these convergence tests computationally favored over others? Oh, wow. I don't know. That's a question of numerical analysis, which Cleve Moeller, of course, was an expert in. I don't know. The trouble is, you see, you can't apply this unless you know the answer. I mean, if you know it's convergent and you know the limit, then you can apply this. Otherwise, so you absolutely have to immediately go to the Cauchy criterion. These things are sort of obvious. This one is, I don't know. I would say that the reliable and extremely general test is the one by Cauchy, or namely that you just say if the partial sums differ by less than epsilon when you go far enough out in the sequence, then you've got convergence, and so you can write a program to test that. Well, what you do is you just, I mean, pick, if you're doing a computer program, then I would start out, I'd set n equals 10 and m equals 20 and see what it was. And then I'd do n equals 100 and m equals 200. And then I'd do a loop, and in the loop, I'd increase by 10 each time. And, with modern computers, you can have the calculation done in seconds. In fact, probably less than a second, and you can see, does this difference essentially go to 0? I'm most comfortable using Fortran. So when I ever have any mathematical problem that isn't trivially soluble with MATLAB or Mathematica, and that's, by the way, in my experience, by the way, you've got two kinds of problem, or three kinds of problems. The problems you can do easily with a little thinking and pencil and paper. The problems where you need to use Mathematica or MATLAB, or, as I should say, Python. And in fact, I encourage all of you to master Python. I've learned a little Python, but I haven't ever taken the trouble to really become a serpent. But what I have found is, at least with regard to MATLAB and Mathematica, that there's a third class of problems, and these are problems that are just too specialized or too complicated to find the answer in MATLAB or Mathematica. And because the space of possible problems is infinite compared to the space of problems that commercial corporations can illustrate and solve in their programs. And so I just write a Fortran program and do the calculation that way. And I find that very relaxing. But it is time consuming, and typically when I do a Fortran program, I've made some stupid mistake, and it's might be 5 or 10 minutes or hours before I debug the damn thing if it's a complicated program. Other people like C, and maybe one can use what is it called? There are so many new languages. Anyway, let me just go on. Here's an example that I encourage you to read, and if you want, I'll do it Wednesday of next week. Let's now go on to another topic which is important, namely factorials and the gamma function. The gamma function is basically the special function. So if you have any positive integer n, then n factorial is by definition n minus 1, n minus 2 down to 3, 2, 1. That's called n factorial. By definition, 0 factorial is 1. And it's not just by definition, it's that you're forced to that, but we'll see that in a little bit later. There are because n factorial is so important, for example, the exponential function, the sine function, the cosine function are defined in terms of power series that involve n factorial. So because it occurs so much, one often needs to know what it is. And there's an approximation due to Stirling, and we'll derive this after we learn about complex variable theory. An Indian mathematician who, by the way, was self-taught and was then invited to England by one of the leading mathematicians at either Cambridge or Oxford. And unfortunately, when someone's invited as an academic, or at least in those days when an academic was invited to England or Oxford or Cambridge, the apartments or the rooms were not heated in any adequate way, and this man Ramanujan had the habit of people in India to dress very lightly, and he didn't have winter clothing, and he didn't have lots of blankets, and he didn't know how to cope with the cold of England. And he actually became sick, and I think he died of pneumonia. So it wasn't a happy story. While he was in England, he was healthy long enough to he might have arrived in the spring, for example, and he had one good summer until English fall brought him down. Anyway, he invented this approximation, which is an improvement over Stirling's. And now an American a theoretical physicist named David Mermin, invented a better approximation, and a second approximation is even better. And then he invented an exact infinite product formula. As I said to you once before, I find infinite products just absolutely fascinating. Whereas an infinite sum I think is kind of dull. Infinite products are quite interesting and fascinating. Anyway, in the book, there's an example, there's a plot that shows you how, where the hell is the plot? Did I skip it? I might have skipped it. Yeah, here we are. So this is the relative accuracy of these approximations. And what we've got here is, this one is, all right, let me get them straight. This one is Merman's first approximation. This one is Ramanujan's, which is better. And this one is Merman's second approximation. And now you might say, well, where's Stirling's formula? Well, Stirling's formula would be off, the error would be off the chart. Notice, however, that all of these approximations, these are relative, this is the relative error. So this is the error, this is the formula for n factorial minus n factorial. So that's the error divided by n factorial. And then that would be a small number, but so I multiply by 10 to the 8th. And so this is the relative error times 100 million. And notice that as n gets to 100, they all converge pretty well. On the other hand, the Stirling approximation is way off, and I couldn't fit it on the graph there. I probably should do another graph in which it's possible to have Stirling's formula there. In any event, so that's the factorial. Now, the binomial coefficient is a ratio of factorials. You must have seen this. So there are various examples here which you can just read. Double factorials are defined in this way. If it's an odd number, the double factorial of an odd integer, positive integer, is just 2n minus 1, 2n minus 3, 2n minus 5, ... 1. If it's an even integer, the double factorial is 2n, 2n minus 2, 2n minus 4, down to 2. And 0 double factorial and minus 1 double factorial have to be defined as unity. So as example, 5 double factorial is 15, 6 double factorial is 48. Now, here's where things get more interesting and more important. You can extend the definition of n factorial from positive integers to complex numbers by means of this integral formula. So z factorial is exactly equal to, or it's defined as, the integral e to the minus t, t to the z dt. And because of the e to the t minus t, this thing obviously converges at large T. At small t, this is essentially 1, and this, if z is a half, things are fine, but if z is something like minus a half, well, it still converges. But if z is something like minus 2, then this is a divergent integral. Now, we'll see that we can actually interpret this much more generally. This definition works for the real part of z greater than minus 1. And in particular, 0 factorial, from this definition, you'd have z equals 0. So t to the 0 is 1, anything to the 0 being 1. So we have integral 0 to infinity e to the minus t dt. Well, that's just 1. So that's why 0 factorial is 1. Now, one of the things that's frankly annoying is that the gamma function, which I think should have been defined as simply the factorial function, so as not so as to make things simple, but instead it's offset by unity. So the gamma function of z is z minus 1 factorial, which is really kind of annoying. And because then if you are dealing with something and you want to go from factorial to gamma function or from gamma function to factorial, you have to remember they're not the same. You have to shift by one, and which way do you shift? And you have to remember, I have to look it up every damn time. Anyway, gamma factorial then is you take this same formula and you just put a -1 here. So equivalently, gamma of z is z-1 factorial, and z factorial is gamma of z plus 1. Now, here is something interesting that's an example of what you'll come to understand as analytic continuation. Let's take the definition of z plus 1, which would be z factorial, and let's rewrite e to the minus t as minus d by dt of e minus t, which of course, I mean, minus d by dt of e to the minus t is just e to the minus t. So this is gamma of z plus 1, which is z factorial. Now down here, then that's times t to the z. Now we then integrate by parts, and we then get e to the minus t d by dt of t to the z. We can obviously drop the term at t equal to infinity. And if the real part of z is greater than -1, then we can also drop the term, the boundary term at t equals 0. And now differentiating, we just get zt to the z minus 1. But now you see, we can bring the z out, and we have then a very interesting and very important identity that gamma of z plus 1 is z times gamma of z. This is for real part of z greater than -1. And so we can keep doing that, and we can keep adding integers to z. And each time we add an integer, we get a factor out in front. So for example, gamma of z plus n is z plus n minus 1 times gamma of z minus 1. So here what I've done is set z equal to n minus 1. I've set z equal to z plus n minus 1. Did I do that? What is it? Right, z plus n minus 1. Anyway, what you can do then is you get this, that gamma of z plus n is z plus n minus 1 times gamma of z plus n minus 1. But then you do the same trick on this one, and you get gamma of z plus n minus 1 times z plus n, I'm sorry, you get z plus n minus 1 times z plus n minus 2, dot, 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 down to z gamma of z. And so for any complex number z, any integers with n greater than m, you can, the ratio of the two gamma functions, which is the ratio of the associated factorials, is just a bunch of products, as long as we avoid negative integers. And if we take this thing and rewrite it, we get gamma of z is 1 over z, gamma of z plus 1. So in other words, we invert this. Gamma of z is gamma z plus 1 over z. And then gamma of z plus 1 is 1 over z plus 1, gamma of z plus 2, dot, dot, dot. And then we get gamma of z plus 3, and then we have 3 factors here. And this works, you see, but obviously you don't want z to be 0 or -1 or -2. So you have to have z. So you expect then, since gamma of z plus 3 in general would be okay, you expect trouble with the gamma function at 0 and -1 and -2. Now, one of the leading mathematicians of the 19th century, Weierstrass, invented this infinite product formula. Well, actually, first Euler, another one of the great mathematicians. I don't know if he was 19th or 18th century. Anyway, he derived the expression that gamma of z is essentially an n factorial divided by a bunch of factors and then n to the z, and that's a limit of that as n goes to infinity. Weierstrass, on the other hand, developed an infinite product formula. And in fact, I can imagine that this infinite product formula lies behind Merman's exact formula for n factorial, because in fact, it looks a lot like it, but I could be wrong. Anyway, another formula for the gamma function, changing variables, is this for real z greater than 0. And then you can show that the gamma of n plus a half is this complicated expression, and also that gamma of n plus a half is this. I don't think we need to do those things. By the way, gamma function, even though modern computers are remarkably efficient at calculating, they give up when it comes to n factorial beyond about 100. I mean, it just becomes absurdly big. And so what you do in that case is you deal with the logarithm of the gamma function. And so there are these various functions, log gamma, L gamma, gamma ln, log gamma in Python, and so forth. They all give log of gamma. That's something that the computer can handle, can calculate very quickly. Let's see, we haven't had a question in a while. Remember, student participation is important. It improves the course. So just in order to educate yourself or your fellow students, please ask a question or ask me to do something that I haven't yet done, or that I skipped over too quickly. This is just a definition, Euler's beta function, and it's what's remarkable about it is that it's so simple in a sense. It's gamma of x, gamma of y over gamma of x plus y. I think we can skip the rest of that. Taylor series. Well, this is something I'm sure you learned in freshman calculus, that if you have a real valued function of a real variable and it has continuous derivatives, then you can write an expansion that f of x plus a is f of x plus a times f prime, a squared over 2 f double prime, dot, 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 and an error term. And the error term, it turns out, is, there's a nice formula for it. It's a to the n over n factorial, the nth derivative at some point x plus y, where y is somewhere between 0 and a, which is sort of an interesting fact. For many functions, the errors go to 0 very quickly, or at least quickly enough, and you can then write this as an infinite sum, and it's an infinite sum with factorials in the denominator, a to the n, f to the n, and then we can rewrite that as the exponential of the difference a times d by dx on f of x. And in quantum mechanics, what we say is that the momentum operator acts from the right on a position bra as h bar over I d by dx of the position bra. So in other words, psi of x plus a, which is the inner product of the position bra x plus a and the state psi, you can write that as this expression here. It would be e to the a, and then I p over h bar. So the I over h bar cancels the h bar over I. And so this is really e to the this is really e to the a d by dx of x psi. So I think about this equation. I think it might demystify some of quantum mechanics for you. I think we make quantum mechanics more difficult for undergraduates and for graduate students by inserting these H bars and I's. They clutter up the expressions in such a way that you get somewhat confused. At least I do. Anyway, in superscript formula, there's a superscript notation for the derivative. This can be the nth derivative with respect to x. And so you can say then that the function f of x and y is this sum going out in the x direction or going out in the x and y directions. You have x to the n, y to the m over n factorial, the nth derivative evaluated at the origin. And this is the nth derivative of f with respect to x and the mth derivative with respect to y, all evaluated at the origin. You can think of Fourier series as power series. The Fourier series looks like this. The coefficients are that. And now if you can rewrite this series like this, and then what you see is that it's two Fourier series. One is with z equal, the two power series. One z is e to the I 2 pi x over L, and the other one is a power series in z inverse, which is e to the minus I 2 pi x over L. Well, these guys are absolutely equal to 1. And so if we do compute the ratio, the radii of convergence of these things, well, we can define r plus inverse as this limit and r minus inverse as this limit, where these are these coefficients, these CNs, and the CNs are given by these integrals. And then we have that the pair of power series, which is to say the Fourier series, converges uniformly and absolutely as long as z satisfies two inequalities. But z is of unit size, and so consequently the Fourier series converges if r plus is greater than 1 and r plus and r minus are both greater than 1. Then the Fourier series converges absolutely and probably uniformly as well. Yeah, uniformly and absolutely. Okay. Binomial series. Well, these are examples of power series. Okay, somebody wants to see example 511. Okay, that's a weird, this one here, you're talking about this 511 because I might have changed the numbers somehow. I might have stuck in an extra example. Okay, all right, well, this is just an example of a uniformly and absolutely convergent Fourier series. And well, the way I got it to be super convergent is I just had these coefficients 1 over 1 plus the absolute value of n to the nth power. So these coefficients go to 0 incredibly rapidly. And so if you compute these ratios here, you get Cn plus 1 over Cn is very, very small. And so you take, so R plus is essentially infinite and R minus is infinite. And so they converge, this thing converges everywhere. I mean, this is super convergent because these coefficients are so small. Okay, binomial series. Well, what you must have learned in college is that 1 plus x to the integer power n is just a sum of the binomial coefficients x to the n, and you can write it this way. By the way, the LaTeX form for this is \choose and then something like curly brackets nk, I think. I forget. Anyway, when you don't know something in LaTeX, you just Google and you enter LaTeX and then what you want, and a screen pops up with several links, and you click on some of the links and you get your answer. 1 plus x to the a more generally is well, it's a Taylor series, and so we take all these derivatives at x equals 0, say, and because the natural thing is to expand about x equals 0, which is to expand about 1 for the function 1 plus x, and so the series, the kth derivative is pretty simple. It just gives us a minus 1, and so forth. So the sum is 1 plus these things, x to the k. And now notice that these are just powers of a, but these, here we have k factorial here, and on the other hand, these things in the numerator here also have k's, so it's not obvious how, to me, immediately how convergent this this thing is, or what the radius of convergence is of this. And I should know, but so maybe I should think about that. So let me write that down. Anyway, if a is positive integer, we get this, but on the other hand, for just real a or complex a, we get this complicated expression. The series, the two of them together, show you that you can write this as x plus y to the a, you can write this way. And if it's an integer, then of course you get this. This is a very important formula. It occurs all over the place, and it's quite important. Neutrino oscillations have been a big deal experimentally for, well, I don't know, 40, 50 years. Logarithmic series, if you do a Taylor series for the logarithm, what you get is that the logarithm of 1 plus x, logarithm of 1, of course, is 0. So this sum starts, for x equal to 0, it's just 0. And you can see then that it's this sum here. If you let x be minus x, you get a sum that's a simpler form. It's something that's exactly negative in this series. And the power series, though, well, it certainly converges for x less than 1 in absolute value. More generally, I'm not quite sure how well it converges. Anyway, the series for the ratio of the two is a simpler expression. There's another topic here, Dirichlet series is one in which the nth term is a funny expression. It's an integer raised to a complex power in the denominator. And so it looks like that. That's a Dirichlet series. So some CNs that are chosen in some clever way, and then you divide by n to the power z. An important example is Riemann's Zeta function, and this pops up in physics every now and then, in particular in statistical mechanics. Zeta of z then is sum from 1 to infinity of, notice the sum goes from 1 because you said n equals 0, you've got an issue here with 0 to the z. So you sum from 1 to infinity 1 over n to the z. or 1 over n to the minus z. This converges for the real, if the real part of z is greater than 1, it converges. And some examples are, some of the zeta functions have very simple expressions and others don't. Zeta of 2 is pi squared over 6. Zeta of 3 is, I think this is just an approximate formula, but zeta of 4 is pi to the 4th over 90. Zeta of 5, so it's these even zetas have nice exact formulas, and the odd ones, well, they may have nice exact formulas, but I don't know what they are. Euler showed that for z, real part of z greater than 1, which is when this Riemann function, well, he showed, no, I'm sorry, he showed that for the real part of z greater than 1, the Riemann zeta function is an infinite product. And again, this is just such an extraordinary formula because it's an infinite product, but not over all integers p, only over the primes. And so this is the thing that makes some people become mathematicians. I don't know. Frankly, I think it's amazing, but it doesn't say anything to me. It just tells me that there's something there that I don't understand and never will. Here's the Planck distribution, and Max Planck showed these things. By the way, Max Planck's son was a young man in the 1940s, and he was one of the Germans who tried to get rid of Hitler. Unfortunately, he didn't succeed, and he was caught, and he was executed. So Max Planck, as an older man, I think, was always a little bit sad. And his son was a hero. Anyway, if you want, I'll go through this. Otherwise, we can leave it till Wednesday. But what you can see here is that in this Planck distribution, we've got a zeta of 3 popping up. The Lurch transcendent, I think we can forget completely. Then there are Bernoulli numbers. Oh, okay, somebody wants me to go through the Planck thing, and okay, that's fair, I think. So what's the Planck distribution? Well, he showed that the electromagnetic energy in a closed cavity of a volume V at temperature T in the frequency interval of width delta d nu about frequency nu is given by this formula. V is the volume of the cavity, H is Planck's constant. With a bar, it's Planck's constant over 2 pi, but this is just Planck's constant, which of course is around 7 10 to the minus 34. So he showed that this was the amount of energy in this frequency range. So if we so the idea here is that you imagine you have, say, a bunch of lead bricks, and you make them into an oven, and then you have the whole thing is closed, and you have volume maybe 1 cubic foot inside and surrounded by lead bricks, and you have a tiny hole, and then you look at through that tiny hole, you stick in a thermometer or some radiation detector, and you then find out what the energy density is and multiply by the volume, and you get this expression. Effectively, the energy density is this thing without the V. So if you compute the total energy, you integrate this. And so we've got to do this integral. Well, the first thing is we change variables, set x equal to beta h nu, and you get this expression. And now I found it easy to multiply by e to the minus x, top and bottom, and I got that. And now you can then think about that. That's x cubed e to the minus x, but 1 minus e to the minus x, well, that's this power series that, in fact, it's the geometric series that we were talking about over here. And it's absolutely and uniformly convergent if x is greater than 0. And of course, x is beta, which is 1 over kt, k being Boltzmann's constant. By the way, Boltzmann was another sad man. He committed suicide for some reason. I don't know his life, but a lot of sadness in physics, especially back there in the 19th century. Anyway, you do this thing then is this infinite sum. And now if you just combine this, you see you've got this sum here. And if we then change variables, what did I set y equal to? I guess I didn't say. But anyway, it's, I guess you set y equal to n plus 1 times x. And so then you rewrite that as this. You do this integral. Well, that's by definition 3 factorial. But then you've got this expression, 1 over n plus 1 to the 4th, but we're summing from 0 to infinity. So if we sum from 1 to infinity, it's just 1 over n to the 4th, but that's zeta of 4. So we've got, so we did have the zeta function in here also. I just didn't see it when I flipped past it. So this is the Riemann zeta function. So you see how it comes about. And then this is the formula then for the total power. And the power density, of course, you just can't divide by V and this goes away. The power radiated is proportional to the 4th power of its temperature and to its area. And what you find then is that it's P is sigma times the area times the 4th power of the temperature, where sigma is called Stephan's constant. And you can derive that from that. The number of photons in a black body distribution at, we call beta, which is 1 over kt, we call it the inverse temperature. What is it? Well, it would be so let's see, what did we do here? The number of photons, right, you see, if we divide by the energy of each photon, we get the number of photons. The energy of each photon is h nu. And so what we'll have is we'll get rid of the h and we'll have 1 less power of nu. And so we get no h, 1 less power of nu. We then do the same razzmatazz, but now we just have 1 over n cubed, which is zeta of 3. And so we get zeta of 3 over 2 factorial. The mean energy of a photon in the black body distribution is, well, it's, you might think it's KT, and it sort of is, but it's actually 2.7 times KT. And you can figure that out by, I guess, just dividing the total energy by the number of photons, and that gives you this expression. So I don't know why I have that stupid Lodgkin ascendant in there, because that's a special function. It's, you know, worth knowing about, but it's probably the last thing you need. It does come up in biophysics, though. Anyway, Bernoulli numbers. These are defined in terms of an infinite series. So you take e to the x over e to the x minus 1. You do a power series for this. And of course, it's x to the n over n factorial times the nth derivative of this thing at x equals 0. And that is the Bernoulli number. So the nth Bernoulli number is the nth derivative of x over e to the x minus 1 for x equals 0. And B0 is 1, B1 is minus a half. The other odd Bernoulli numbers are all 0, and the even ones turn out to be given by Euler's zeta function. And remember, the even values of the Euler Zeta function. I call it Riemann or Euler zeta function. This should be Riemann, shouldn't it? All right, let me fix that later. I am terrible with names, and so I just don't pay much attention to what people or things are called, and every now and then it catches up with me. Anyway, they occur in various cases of expansions for power series for transcendental functions like the hyperbolic cotangent. We've got these beta function, Bernoulli numbers. There are Bernoulli polynomials where instead of having x over e to the x minus 1, you have e to the xy, and then you get this there. Some people define Bernoulli numbers slightly differently, so you need to make sure that you know which one is which. By the way, the NIST, which used to be the National Bureau of Standards and now is the National Institute of Science and Technology, I think, NIST, they have a nice website that has a lot of useful stuff about mathematical physics. So special functions, values of parameters, for example, the latest value, the best value for the gravitational coupling constant, Newton's constant, you can find it there. And in fact, the value there was better than the value given by the particle data group. And so I actually I think I sent email to those people. Anyway, asymptotic series. This is a trickier concept, and it's kind of vague. In my mind, at least, it's kind of vague. So suppose we have a partial sum like this. The nth partial sum is a sum up to n of ak over x to the k. And we can think of this as an asymptotic expansion for a real function. And how about, when is this a decent expansion? Well, suppose the remainder, or the error, is the difference, of course. And suppose the error times x to the n in the limit n of x going to infinity is 0 for fixed n. And so then we can say f is sort of the sum from k to infinity of 8k over x to the k. So it's equality in this sense, namely that this series is really good as x goes to infinity. And you see, as x goes to infinity, it's the first few terms that are important. An example is a function called e sub 1, and it's defined this way. And you can then get an inverse power series expansion of it. Power series in 1 over x looks like this. And you then find that indeed it is an asymptotic series. It occurs often in physics when you've got a small parameter, lambda, say, and so instead of 1 over x, we just have some small parameter lambda. And we say, well, it's a good approximation of lambda, 1 over lambda to the nth power times the error is 0 as lambda goes to infinity. Here I say that Dyson's series, or the WKB, are asymptotic in this sense. Actually, I think we wish they were asymptotic in that sense. I don't think anybody knows if the Dyson series is actually asymptotic in that sense. We think of them in that way. Yeah, all right, so somebody here is pointing out something interesting, that NIST has wallet cards that we can get. So I guess you either print the thing out or you send them an email and they send you one. By the way, Dyson Freeman Dyson died just a couple of weeks ago, or maybe it's a couple of months ago now. He lived to be something like 95, and he was sharp as a bell until almost until his death, actually. He was at the Institute for Advanced Study for a very long time. And the story I heard about him is that when he was at Cornell, he would show up at Cornell with the New York Times and would sit at his desk reading the New York Times much of the day. And yet he wrote one of the leading papers in quantum electrodynamics back in 1947, something like that. And explained how you could relate Schwinger's description of quantum electrodynamics to Feynman's description of quantum electrodynamics. And the story, another story I heard was that he and Feynman drove across the country together, and so they probably learned quite a bit from each other. They must have had some very interesting conversations. Okay, fractional and complex derivatives. Well, this is something I added. I don't know if you guys really need to know that. If you want to hear about it, I'll be happy to do it maybe Wednesday. It's just a different definition of a generalization of the derivative, and I'll skip it for now. These are examples of electrostatic problems. I don't think we need to go through this. If you want, I will certainly do it. Here we've got infinite products, and these are some infinite products that it's good to know about. I don't think we need to derive them, but here sine of z is z times this infinite product from 1 to infinity of 1 minus z squared over pi squared n squared. I mean, this is just an absolutely remarkable formula. And I think it's mathematical magic. And the same thing with the cosine formula, the sinh formula, the Cauchy formula. And these formulas are magical in, I think, kind of the way in which path integrals are magical. Feynman, of course, was the one who invented path integrals, and I think people poo-pooed them for quite a long time. And in fact, I think he invented them in his thesis, although it might have been that Dirac invented them also, or thought about them somehow. Dirac, of course, was just an incredible man as well. So anyway, we're basically out of time. Does anybody have some last question? We seem to have gone through chapter 5 and more quickly than I intended, but on the other hand, I don't regret it. If you want, ask me on Tuesday or Wednesday to explain some part of chapter 5 that I went over too quickly, but I think it's much more important for you. Chapters 6 and 7 are vastly more important for you as physics graduate students and as practicing physicists. So, all right. If nobody has a question, then I'll just end the recording and put it on on YouTube later tonight. I did put the new homework assignment. I modified the current homework assignment and put a new homework assignment on the web page. The new homework assignment is one that if you go through it, it's a little, first two problems I think are a little tedious, but they're worth doing because I think you'll learn a lot of quantum mechanics doing those first two problems. I think they might make some things real for you that in class might have seemed wishful thinking or abstract or something. All right, I'm going to end it now. And I'm going to say goodbye to everybody. I'm going to